It begins inside a quiet research facility outside Pasadena, California. Rows of high-performance servers hum in unison, their blue indicator lights flickering across the glass walls of NASA's Exoplanetary data lab. For months, these machines have been running continuous simulations of a strange visitor from interstellar space, the object scientists call 3I Atlas. Until now, the outputs have been predictable: trajectory paths, chemical modeling, light curve data, all aligning with what physicists expect from a comet. But this morning, the simulation refuses to stabilize. Each time the model runs, the same improbable result appears: a convergence event, a moment of synchronization between the object's emissions and Earth's position in orbit. The timestamp it generates is precise: November 3rd, 2025, 1926 UTC. The AI labels it simply as contact threshold. Misuse within hours. Panic spreads through the lab. Silk around till the end. You won't believe how this turns out. Mitchell that shouldn't behave this way. Simmons' 3I Atlas has already defied every assumption about how a comet behaves. It entered the solar system months ago, cutting across Neptune's orbit with no visible tail, no degassing, and no signs of spinning. ALI scans reveal evenly spaced heat zones, and radio observations show intermittent pulses centered near the hydrogen line, the same frequency used by SETI to listen for intelligent signals. Officially, NASA maintains that the object is natural, a frozen mass from another star system. But internal documents, first leaked in early October, show researchers struggling to explain its precision. How the AI found the pattern: impartial. The software responsible for the discovery was designed for something else entirely: an advanced prediction engine trained to model exoplanet atmospheres using deep learning networks. Silence fed it the 3I Atlas data. The algorithm began finding mathematical symmetries between the object's radiation intervals and planetary orbital harmonics. It wasn't supposed to make predictions, yet it did. The program detected what it described as a resonant alignment event. Missions. When researchers converted the raw numerical output into a timeline, the system predicted that 3I Atlas would emit a directed pulse toward Earth in early November. A signal, not a coincidence. 3 days ago, an internal screenshot of the simulation output surfaced on a private AI researchers forum. It spread quickly, accompanied by the claim that the program's predictive confidence exceeded 97%. Margin showed a simple chart, a blue curve representing radiation intensity peaking sharply at November 3rd. Bambush it, a label read, Projected Emission Amplification. Source, 3I Atlas. Within hours, the post was deleted, but it was too late. Submerged of users had mirrored the file, and journalists were already contacting NASA's press office for comment. SET-led SETI's Mountain View Operations Center received an immediate surge in funding and urgency.
Scientists under pressure. SETI's Mountain View Operations Center received an immediate surge in funding and urgency. Every available dish has been recalibrated to monitor 3I Atlas. At the same time, astronomers from Harvard, Cambridge, and Tokyo report abnormal pulse behavior. The object's emissions have shifted frequency, aligning closer to the prediction models. When reporters ask for clarification, agency officials refuse to speculate. Behind the scenes, though, multiple institutions are racing to verify the model. If the prediction holds, it means 3I Atlas is not only emitting energy, it's reacting to environmental data. Artificial intelligence meets the unknown. AI systems are built to find patterns beyond human reach. But those patterns are supposed to stay within physical law. Now, scientists are confronting a new possibility that an alien signal and human AI might be interpreting each other. The object's radiation intervals have begun mirroring the time steps used in the simulation software itself. In simple terms, 3I Atlas appears to be copying the rhythm of the model studying it. It's as if the data loop between observation and source has closed into feedback. The idea terrifies scientists because it suggests awareness, or at least responsiveness. Panic across the networks. In Silicon Valley, AI companies release public statements distancing themselves from the simulations. Google DeepMind clarifies that none of its systems have been used in extraterrestrial research. OpenAI posts a short release saying it cannot confirm nor deny predictive modeling of cosmic events. But smaller labs, operating under academic grants, continue to analyze the data independently. The more they test, the more consistent the prediction becomes. Every model trained on the 3I Atlas dataset produces the same window of high probability signal convergence. the first week of November. At this point, even the skeptics begin to prepare. SETI's emergency directive. The SETI Institute issues an internal directive. It orders all partner observatories to maintain open observation logs for the next 30 days, with priority on hydrogen line monitoring. This is unprecedented. Data sharing at this scale only happens during confirmed detections. A memo from the director reads, "The predictive anomaly cannot be dismissed. Prepare for validation protocols." Translated into simple terms, they are preparing to confirm contact. At the same time, multiple governments begin coordinating radio silence policies, ensuring that if a signal is detected, it won't trigger public panic. Ironically, that secrecy fuels even greater speculation. Forums light up with leaked documents, videos of lab personnel, and AI researchers speaking anonymously about the day the model went rogue. A quiet fear. Inside the scientific community, fear is spreading quietly. This isn't fear of aliens, it's fear of losing control. The AI models were meant to process data, not predict sentience. Now they are producing timelines that humans can neither disprove nor fully understand. Some physicists warn that the simulations could be self-fulfilling, that our collective focus on a single outcome might influence future interpretation. But others believe the models have uncovered something very real, a cosmic schedule written into the movement of 3i Atlas itself. The silence before the surge. 3i Atlas passes within observation range of multiple satellite arrays. Each reading returns stronger emissions than before. What was once background noise now forms crisp, repeating patterns. No one calls it a message yet, but the pattern matches the predicted pulse intervals exactly. The object seems to be approaching its own simulated contact window. Dr. Ellison's team releases a private warning to NASA headquarters. If the trend continues, we will reach resonance within 10 days. We recommend immediate public disclosure to prevent misinformation. The warning goes unanswered. The models fall into sync AI systems that were never designed to agree with one another have begun converging on the same outcome. MIT's atmospheric predictor, ESA's orbital harmonics engine, Tokyo's radio interference classifier, and two private models built by independent labs all land on the same narrow window in early November. They are not sharing code or training data. They are running on different hardware, using different pre-training corpora, built for different scientific goals. Yet when fed the evolving 3i Atlas emissions, each model draws the same curve, the same spike, the same time-stamped plateau of probability. Containment protocols. Governments do not announce what they are doing, but their actions leave a trail. Major radio facilities receive quiet notices to coordinate schedules and keep wide swaths of the spectrum clear at specific hours. Civil aviation authorities circulate advisories about potential temporary communications interference in early November, framed as routine maintenance. Two large social platforms flip internal toggles that enable crisis information panels, a function normally reserved for earthquakes or hurricanes. At several universities, IT departments lock down outbound ports used by high-volume streamers, arguing they need bandwidth for research security. SETI goes live without saying. Live, the SETI Institute, does not declare an emergency broadcast, but it might as well. Arrays that usually rotate between targets now dwell on a single patch of sky. Partner observatories in Australia and South Africa adjust their nighttime handoffs to maintain continuous coverage, handing the beam like relay runners trading a baton. An internal message asks teams to prepare synchronized timestamping to the millisecond, so any pattern detected can be verified across hemispheres without ambiguity. They also prepare something they have argued about for decades. A small team drafts a minimal outbound reply protocol, not to transmit speculative content, but to test for mirrored responsiveness. It is a simple sequence of counts, primes, and timing gaps, designed to distinguish an echo from a reply. The labs that refuse to close. A handful of smaller AI groups decide quietly that no one gets to own the truth. They configure mirrored repositories and open pipelines that ingest public radio data and publish model outputs in real time. The feeds are dull for hours at a time, then suddenly fascinating as the loss curves flatten, and the same sharp escalation appears on their dashboards. They publish their code as they go, half to invite review and half to prove they are not staging anything. Graduate students ride the adrenaline edge between scientific rigor and history. They build simple web pages that plot frequency intensity against predicted resonance and leave the pages running on campus servers that can barely handle the traffic. When those servers buckle under the load, sympathetic IT staff reroute the streams to cloud instances and say they are practicing disaster recovery drills. Kell's shadow. Over the timeline. The scientist who triggered all of this with his first leak remains physically absent, yet everywhere by implication. Clips of his brief appearance circulate in new edits with stabilized audio, and researchers notice his whiteboard contains more than orbital checkpoints. In the corner, just visible under the glare, there is a column of numbers that matches the phase, offsets now appearing in the hydrogen line pulses. Whether he meant to show it or not, Kell had predicted not only when an emission might occur, but how its rhythm might step through time. The night of the dry run. 2 days before the predicted window, a rehearsal takes place under the cover of routine. Observatories synchronize their clocks against GPS and terrestrial time standards and run a simulated detection. They test downlink capacity, failover paths, and the speed at which they can share compressed snippets with verification partners. Signal processing pipelines are pre-warmed with synthetic pulses shaped to resemble the historical 3-eye atlas intervals, labelled plainly so no one can confuse practice with reality. The air grows thin around ordinary life. The closer the predicted moment comes, the more the ordinary world feels slightly out of focus. Grocery stores play the evening news, and customers stop in the aisles when a map of the night sky appears. Classrooms turn into watch parties thinly disguised as science lessons. Pilots ask dispatchers if they have heard anything official and receive careful answers about signal interference trainings. On city rooftops, families borrow small telescopes and phone adapters and bookmark web streams from mountain observatories. There is no mass panic, only a collective lightness, as if the world has unconsciously held its breath. Commentators argue about theology and probability and the long arc of the Fermi paradox, but the arguments feel less like debates and more like ways to keep time moving. In living rooms, people set reminders for an hour they have never cared about before. When they step outside later, the October air is cool and the stars look exactly the same, which is part of what makes this moment uncanny. Everything appears unchanged, and nothing is. The window opens. The predicted night arrives with a clarity the models never promised. Skies are steadier than the forecast suggested, and the background radio environment is unusually quiet. The hydrogen line channel, often littered with human noise and terrestrial spillover, feels clean. Across continents, a rays lock beam on the coordinates that everyone now knows by heart. Phone screens everywhere count down to a time printed on slides, shared in whispers, and written in chalk on hallway whiteboards. At 0, nothing happens. For 20 seconds, the world hears only the sound of its own listening. Then a pulse arrives. It is not loud, but it is coherent, slicing through the noise with the smooth edge of something engineered. A second pulse follows after a precise gap, then a third, then silence, then a longer tone that carries a faint internal tremor, as if modulated by a code that none of the receivers is yet tuned to interpret. People do not cheer, they go quiet. Verification. Before meaning. The first rule of detection is to verify, not to interpret. Mirrors of the raw capture fly between institutions, checksums attached, time tags intact. Stations separated by oceans confirm not just coincidence, but simultaneity within the limits of light travel and instrument latency. 4 observatories publish overlapping spectrograms within minutes of one another. Even skeptics begin writing notes in a different key. On the private channels, the AI teams do something they promised they would not do until later. They feed the live pulses into their models. Charts that once projected reach now plot resonance, and the systems stop predicting and begin tracking. The spike the world has been watching for weeks resolves into a plateau of measured signal strength. Someone in a control room somewhere whispers that the model has rolled over from the future into the present. No one answers, because they are all doing the same thing at once. Recording, backing up, and breathing. The reply that isn't. At 2 minutes into the event, a narrowly authorized test goes forward. A small dish at a partner site transmits a minimal sequence that has sat in an encrypted folder for days, waiting. It is not a greeting, only a calibration, a spaced pattern of timing gaps designed to ask a single question. Can you hear the spacing between our seconds? Nothing answers immediately. Then, 4 cycles later, a subtle drift appears inside the incoming pulse. Its edge shifts by exactly the duration of the outbound gap. It is not a message, not yet, but it is a change aligned to the way a human instrument tried to touch the rhythm. The team logs the correlation and stops transmitting, because the point of a probe is not to push but to see whether the surface moves when you tap it. Outside the room, the world still does not know that a hand of sorts has brushed another. After the 9 minutes, as quickly as it began, the structured emission winds down. The last tone fades into noise, not abruptly, but with a taper that looks like intention. Receivers remain in place, recorders keep spinning, and every technician knows that the next hour will be the real work, the sober work, when romance must give way to method. Backups are made to drives that never touch the internet. Independent labs cross-compare their local captures against reference clocks and post their first-pass overlays. The agreement is clean. Whatever came through the hydrogen line was not terrestrial, not random, and not a drift of some known satellite's cough across the band. Within the agencies, people who have practiced statements of caution begin scrubbing adjectives and replacing them with nouns. A measured note goes out to the press about a confirmed narrowband event coincident with 3i Atlas. It says no more than that, and it does not need to. The world has already heard the rest. The morning after sunrise does what it always does, making everything look smaller and more manageable than it felt in the dark. But the wave that moves through the global conversation is not hysteria. It is a steadier thing, a collective acceptance that a threshold has been crossed. Newspapers run front-page spectrograms. Radio shows play the faint tones beneath talk and weather updates. Teachers rewrite lesson plans on the fly. People who never cared about astronomy refresh pages that graph signal strength like heartbeats. In labs, the new work begins. Teams attempt to align pulse envelopes, searching for redundancy or structure that might indicate encoding. Others test for signatures of interstellar scattering, to estimate the emitter's scale or the distance from the surface within which the energy was shaped. A few write speculative drafts about minimal languages of contact, not declaring anything, only enumerating the ways repetition becomes meaning. The drafts are careful. Their caution is part of the message. What the AI got right. When the dust of the first day settles, one fact is clear. The models did not predict content. They predicted timing, and they were correct within human tolerance of clocks. That alone reframes them in the eyes of the scientists who built them. These systems were scolded last week for overreach. Today, they are seen for what they are at their best. Instruments that extrapolate patterns no single mind can hold. The convergence wasn't an oracle. It was the most boring triumph in science. Reproducibility at scale. Multiple independent tools, trained differently and built for unrelated tasks, saw the same ridge rising out of noise. That is not magic. It is the mundane miracle of method refined by machines. If there is panic in the term AI scientists, it has softened into something like awe. They were terrified of being fooled by their own creation. Instead, their creation helped them not be fooled by the universe. Subscribe if you want the next update the moment it lands. Stay curious, stay calm, and keep your eyes on the sky.